So this is a post-Capstone summary presentation. Group members were Michael King, myself, Samuel Redikoff, and Lucas Carbone Lepsch. This presentation is for those that I've discussed the project with, but I didn't really explain it all that well, or they only ever saw like a few pictures of various items from it. So this is for that, to kind of give an overview of this project and how it went and what we accomplished in the end. And this is also for members of the University of Regina engineering faculty that only ever saw this project to partial completion, and this is to show that we did actually finish this. So with that, our client was the South Saskatchewan Kart Club. They are a small go-kart racing group that operate just outside of Regina, Saskatchewan. At the beginning of our fall 2023 semester, the Kart Club had passed on to our professors some basic requirements of things that they wanted. So what they wanted was to modernize their track with some sort of light signaling system. They wanted some wireless signaling lights, some lights at the start line, some sort of lap count display at the start line, and then some also at that same place, some sort of light up last lap sign. Midway through September, Braden Massey, a member of the Kart Club, he came and presented this project in a bit more detail. Braden had graduated from the University of Regina in electronic systems engineering a few years before my group did. He acted as a liaison for the Kart Club for us, as well as a technical advisor. Towards the end of September, our group went on a site visit on September 24th, 2023 to gather some more information about just generally how the track operates, but then also to give some context to the different items that they wanted to build and just to better understand some things. So this is the westbound pit lane. This is primarily where the racers start from. They go out here, they do a preliminary formation lap, and then they actually start the race. This is that same pit lane, it was just a different time of day when it was cloudy. There's a different angle to get a better view of some of the track out there and the vastness of it. So this is the primarily, first the eastbound pit lane, so they can race from the other direction if they want, depending on the race requirements. As well, you see there's a catwalk above there, and then on the left side of it, there is the race director tower. This is where the race director stands, waves the start and end flags, and then also can talk on his radio if he sees problems along the track. On the other side of the catwalk is a CCAN. This is the timing booth. So the karts do use a Bluetooth system. I don't know if it's only just at the start line or if they have other points around the track, but basically it's just to try and give some real-time stats for the race. Again, not exactly important to us necessarily, but in the CCAN booth, they also do have that controller for a light that is already installed at the pit lane that was created by Braden. We can see that controller here. Very nice looking. And then also up in the top corner there, you might just be able to see the red and black boxes. That is the MyLapse kart tracking equipment. On the race director tower here, you can see this last lap sign. Basically, when the last lap starts, the race director unlocks that sign and swings it out. As well, there is a generator at the track, and mainly it's for powering stuff inside the timing booth CCAN, but the Kart Club said they would allow access to it for anything that's inside the CCAN that we make, or anything on the race director tower. It's not really feasible to run AC power out to anything else on the track, but at least we do have access to a generator for some things. This is a Marshall booth. There's 3 of these around the track at the 3 dangerous corners, and then of course nearby to this will be where the lights are, or very close by. But basically they're currently the racers, the marshals just sit in here, and then if they need to, they'll grab one of their colored flags to signal to the drivers what they need to signal. Another important thing that we did when we were at the track was to check what frequencies were busy by using this handheld spectrum analyzer borrowed from the university. This is a Google Maps view of the track. It was important just to get an overview general shape, but then also we use Google Maps here to plot some approximate distances. As you can see, some different points marked in black where like the marshal booths are around the track. This allowed us to create this diagram here, where we marked where the marshal booths are, and then also down towards the bottom here where the race director is, and we can see all the different distances between all the different points or nodes in the system. This allows us to know what distances we need to work with to achieve reliability. With that, I will now show here some video footage that we took at the track to also just get a better sense of how the track operates. Okay, so here we have some racers going up from the pit lane. This is the perspective of the tower. And then here we go again, but from one of the marshal booths on the ground. They come up from the pit lane and then go around this first curve, obviously. So they're just doing the formation lap right now. So they just get some practice before they start the race. And they still have to warm up their engines, etc. And here they go. They're at the end, coming towards the end of the formation lap along the back straightaway. They are just getting into a formation here where they bunch up. And then they're coming around the back straightaway corner, down the side of the track. And then you see more of them bunch up into the formation there. And now they will be coming along the front straightaway towards the start line, where they will be judged by the race director. And here the race director is given authorization to start the race. And then here's from the perspective of the tower. And you see the racers, they're coming down the side there, approaching the corner onto the front straightaway. And you see they're getting into formation. Here they come. And now start the race, because the formation was good. So now they're on lap 1. So now this is later in the race, kind of towards the end. You'll just see here, there's a marshal standing there. She's holding a yellow flag. She's bunched up because there's nothing wrong with it. She has there just in case it's needed. And now here, this is approaching the very end of the race. Follow at about the distance there. And that's first place there, with the race director waving the checkered flag to end the race. And here comes second and third, and there's the checkered flag waving again. The signal end of race, or finish. And then here's the same perspective, but from the tower. Very far behind here, but the first place person will come up here in just a second. Not quite yet. And then here's first place. There we go. And second and third will come around here in a second. There's second and third. Again, the important thing is that they're using the checkered flag. No fancy signal lights or anything. Old school stuff. Nothing's not terribly wrong with that. But in here's perspective, you can see the race director likes to be on the ground sometimes, not necessarily on the tower to signal end of race or to start the race. Okay, so after visiting the track and collecting all this information and video footage, ultimately, we wrote down some important observations. This is kind of a summary of them. So the current track setup uses some very old school flag signaling systems, where the marshals will give like a green for good to go, yellow as a caution or slow down, red, stop the race because something catastrophic has happened. This has very rarely been used. And then blue, pull to the side because somebody's trying to pass you. The race director, of course, uses flags from his tower to signal various points of the race, such as start or halfway. and then of course the checkered flag at the end there. There's of course the physical last lap sign that swings out from the tower, and then of course we also noted the pit lane light that was previously installed by Braden. The current system is quite dangerous for the marshals because of the high-speed nature of the carts, and that the marshals have to be physically close to the track for the racers to see their flags. When a marshal is preoccupied helping a racer that's like spun out or crashed, it means the corner is not occupied, and that can cause a dangerous situation. And the race director currently can only yell on the radio if something even worse is happening. The pit lane is currently controlled, as noted earlier, by the timing person in the timing C-can. So the race director has to go on the radio or just yell down to the timing person to change the pit lane light color, which isn't exactly convenient. Ultimately, this translated into items that we decided need to be built to meet their requirements. So number one, wireless lights. And from our observations, we wanted them to be controlled both by the marshals from the marshal booths and by the race director in his tower. Number two, some small portable controllers for the marshals, later called marshal controllers, that control just one light group or channel set at a specific corner. Three start line lights for the race director. We talked to them and they wanted three. So 3 start line lights at the race director for initiating the race. The race director wanted this one specifically when he talked to us. So he wanted a portable race director controller that can control the start line lights and the emergency stop all red. This is to allow the race director to be mobile, to be able to stand on the ground next to the track when he's starting or ending the race. Number 5, we want to do this one just to make the system a bit more complete, but we wanted to integrate the existing pit lane light into our system. And then number 6 and 7 is the lap count indicator sign and last lap indicator sign and the lap count display. We later determined and talked with them that we could actually take these 2 items and combine them into being the same item. I'll talk about how that works a little bit later, or quite a bit later in this video. And then finally, of course, the master console that's in the race director tower that can control everything. The university required us to make some technical specifications for our equipment to meet. So a race day is typically 10 hours long, so minimum 10-hour battery life. A response time of 1 second. So to qualify what that means exactly. So you press a button on a controller, whether it be the master console or a marshal controller, and the correct light or group of lights and the correct color turn on within 1 second. A wireless range of at least 200 meters. That is to fulfill that diagram of distances that we had earlier, and then some. Enclosures must be at least IP54 rated. So, as a note, the university only marked us on the design of our circuit boards, basically, and the process that we went to get there. So we get no extra marks for actually designing enclosures, but because this project required us to make like a semi-finished product, not just some very prototypey looking thing, we still needed to make enclosures for this. So looking at IP charts online and considering the fact that they race sometimes in light rain conditions, we deemed IP54 to be the bare minimum that we would need to meet to operate in those conditions. And then, of course, the lights and lap counter must be visible on a sunny day. So some basic decisions needed to be made before we could design things. Some of these were made right away, and then others were made as we went along and encountered them. So, 1, wireless network standard. How is the master controller going to actually work? How is it going to, control everything? Wired network. Surface mount or through hole parts, what microcontroller we're going to use, and of course, what antenna will we use. So some wireless options. So we could have used cellular, so like LTE or CDMA. There's a question, though, of complex implementation. Would there be licensing fees or problems? Again, and then, of course, I repeating myself, but like recurring fees the car club would have to pay to access the network. LoRa was a big contender. It's a very long range but low data rate depending on the distance that you go at. But there's a question, of course, of latency in the real world. And then, of course, because LoRa is not a mesh protocol, would be quite a bit of work on the microcontroller's end to do the mesh protocol stuff. Z-Wave was considered for a while, but it was they had certain limitations with like how many hops on the network a packet could take. And it was also not the most well-supported or popular protocol, so would we be able to get replacement parts later, or if you wanted to build more equipment later, would you be able to get the same radio, etc. Then, of course, there's old school RF radios of the 315, 433 megahertz variety. I did do some experimenting with some little RF transmitters that I had laying around that were paired with some little remote controllable electric relays. And I kind of deemed that this would be a question of reliability. And then, of course, because it's not a mesh network, there'd be a lot of overhead for the microcontroller to sort out messages and just to do the mesh protocol. So we settled on using Zigbee. It does, though, have an issue of a fixed central node that we'll come back to much later. So the radio that we ended up getting, and I'm glad we went with these lines of radios, is so Digi International is a very popular vendor, seemingly, of networking and IoT equipment. They make a line of radios called XBs. XBs use this form factor, and then they can implement many different IoT protocols, in this case, the Zigbee protocol. With this, of course, we did borrow some XBs from one of the faculty members, but those ones had an integrated PCB antenna on them. From doing testing, we deemed that a PCB antenna would not have the appropriate range needed for our system. So to make sure that things were rugged and reliable, we went with one that had a big RP-SMA antenna connector on it. We could have also gotten ones with little UFL antennas on them, but those are tiny, fiddly, and fragile, and we didn't want things to break easily, so we went with a big RP-SMA connector, so we could connect up some proper antennas to this thing. So, master controller architecture. So there are kind of two options that we debated. So, monolith single board, where one microcontroller does everything. And then ultimately we went with a distributed control idea, where you would have separate boards for each sector / other functions, and then those would be daisy chained together, and then coordinated by a coordinating board. So of course, these will all be daisy chained together by some sort of wired medium. We'll get to that later. But then with this wired medium, when we were figuring things out, so the master controller, of course, would be sitting in the range director tower, but then close by below it would also be the last lap sign or lap counter, and then of course the start line lights. And so we ultimately decided there that it'd not be worth making the start line lights wireless, or also the lap count or last lap indicator wireless, because they're in close proximity to the master controller. So it would just be better if we could just take some sort of control or wired cabling and just run it back up to the master console there, since they're in close proximity. So ultimately, we just determined that the wired network would also have the start line lights and lap count display live on it as well. So for the wired network itself, for connecting up all the for wiring up the master console as the distributed network and the start line lights and lap counter, etc., we just decided to go with a RS-485 half duplex transceiver. This seemed kind of like a no-brainer, relatively simple to implement, and in the end very reliable. But basically, RS-485 allows to 100 kilobits per second at around 4,000 feet. Again, we didn't remotely do 4,000 feet, but good to know that you can do that. Initially settled on an SP3485 chip. This was used on a SparkFun breakout board that I had used before for some experiments and for some initial testing here as well. But this chip only allows up to 32 transceivers on a bus, which honestly would have been fine. But Michael found a better one, the SP3078, which allows up to 256 transceivers on a bus. To complete this, of course, we used some RJ45 jacks / couplers, again to make the physically connect up the daisy chain, and then of course with that Cat5e cabling as the transmission medium, with a characteristic impedance of 100 ohms. This is close to the spec of RS45 of 120. And then on the open ends of the network, we did use some 120 ohm termination resistors. And then of course, RS45 only defines physical and electrical specifications, so you do have to write a protocol to run on top of this, but that's fine. Service mount or through-hole components. So the Kart Club intends to expand the track later, either by adding more sections to the track, by physically, adding more pavement or more track, or just add more lights to the current setup that we're going to build for them. So either way, they need to build more equipment in the future. So we deemed it, just keep it simple, use through-hole components to make board assembly easier for novices. So that's fine. We mostly stuck with this. There were a few surface mount parts that we did use because we couldn't either find an equivalent in through-hole, or we just didn't deem it worth it for space reasons to do through-hole. So, but of course, the packages that are surface mount are a little bit easier to solder, so it shouldn't be too much of a problem for them later when they want to make more equipment. The microcontroller was an Aviar 128DA28. It is a through-hole DIP package, so it's easy to replace if something breaks or when they want to build more equipment later. 128K flash, 16K RAM, and then a 24 megahertz clock. This wasn't the best decision, and it was kind of came down to our initial implementation of the programming interface, and then, of course, the use of Arduino as the programming environment. But we did later fix this. For the antenna, we came up with some specifications to search for. Basically, outdoor rated, because we want to use this outside, obviously. Omnidirectional to make sure you can get reception no matter where the antenna is. Vertical polarization is quite common among equipment, so we went with a vertically polarized antenna. And then basically just maximum gain we could find. Note the university did put a limit on us of a maximum gain of plus 30 dB, which is like a lot. So basically it just meant avoid active antennas. Again, this is for safety reasons. You didn't want to cook yourself in the lab with RF accidentally if you're experimenting. So after some searching, it came across this nice antenna, quite large, has a gain of 9 dB. I assume that's peak. It does have, of course, the RP SMA connector on it for connecting to those to our equipment. Some more information on it. With that, of course, the actual radios would live inside the enclosures, and then to connect them to the outside world, you would connect up this little RP SMA extension cable. In this case, we've got a 4-inch version of it, and then the antenna would connect onto that. To try and weatherproof or / waterproof stuff, we did also make sure we got some proper rubber seals or O-rings. And then for the master console, to make antenna placement a little more flexible to work with that tower, we did also pick up this magnetic base or stand, and that would screw into the outside of the master console, and then you'd connect the antenna up to that. All right. So additionally, during the semester, the university also got us to do some additional work with getting some basic outlines made of how our stuff will actually work. So this is a basic architecture idea that we had. initially. There were some other things that we did after this as well. But ultimately, later in the semester as well, we did give an update presentation to the CART Club in November to kind of talk about our progress and to kind of see what where did we go from that September site visit. So we gave them an initial cost estimate of about $3,760. And then we also presented some initial concept ideas for certain equipment, such as wireless light. So again, you could have it on a post, some sort of mounting post, and then there'd be a battery box at the bottom for powering it. And then of course the actual light itself, it could be on a swivel mount. Again, this is a very rough sketch and kind of an idea for them. And then of course there's a big antenna sticking on the top of it. This one we got a lot of feedback from them. So this is the initial master console slash start or race director tower start line equipment stuff. So the initial idea for the master controller would be we'd have some sort of master unit with possibly a display on it, and then each separate controller or function thingy attached to it would be in its own separate enclosure. Like this would be a pit lane light controller. Channel 1, 2, 4, 3. Again, all these would be in separate little boxes for controlling. From there, of course, then of course it'd also be the lap count controller of some sort. And then of course this pit lane light, starting a light, and these lap count, that would still, and then of course that would all be in separate enclosures. They came back to us and said, okay, could you take the master unit, this pit lane controller, all these channel cards, and the lap counter, and could you just take, or lap count controller, and could you take all that and combine it into just one enclosure? And we're like, yeah, okay, that makes sense. We can do that. And then of course there's the pit lane light and the start lane light and the lap count or slash last lap indicator. Those would still all be separate. But that was a good point that they made to us. It'd also make manufacturing a little less complicated. This was a concept Marshall controller. They came back to us and clarified, okay, nix the red stop button because only the race director can issue a red flag. So that would stop marshals from ever accidentally issuing an emergency stop red flag. So that would cut it down to just a yellow caution, a green for go, and then a blue for somebody's trying to pass you. There'd be some sort of device status, which more or less just became battery indication, and then some sort of network connectivity indicator as well. So later, this culminated in 6 board designs that we used to ultimately make all our equipment. So this is kind of now towards mid to end of December. So 2 kinds of signal light driver boards, and we'll talk about why in a minute. A Marshall controller board, master main board, button module, and last lap counter. So basically, the process for this was, as we went along, basically break down what functions or blocks does the board need to have, then figure out a circuit that can implement that function, and figure out, and then also how that connects to the rest of it. Of course, this circuit usually is something that we've had experience doing before or learned in class. And then we try and reuse this circuit across as many boards as possible. Again, to get bulk discounts on parts from when we order from the vendor. And then also, kind of same design language for everything and similar layouts so that it's easy to try and understand things across different stuff. And then, of course, we would break that down to find appropriate components to implement each function. So another thing on powering, how to supply power to devices. So the wired devices ended up being a little bit complicated, but it was also somewhat elegant in certain respects. So the wired devices, of course, have access to a 50-watt, 12-volt AC to DC power supply, and that power supply is what connects from the master console to the generator. Low power devices, and we'll talk about what is a low power device later. We decided could be powered by the Cat5 network cabling. So to talk about that, The RS-485 signal only ever used one pair of wires inside the Cat5 cable. So we decided, well, we could use the other three pairs to send 12 volts power and ground to some devices. This would also allow cleaner runs of cabling for certain things, because then you wouldn't have to run separate power and data. It would just all be in the same cable. Higher power devices did end up using a positive 12 volt supplemental power wiring that was, I believe, 18 gauge wire. I'd have to check. It was Dave that ordered this wire for us, that, rated to be outdoor and stuff. When you're using a high power device, both screw terminals on the PCB must be populated to allow for power daisy chaining, so that way power could be passed on to the next device that needs supplemental 12 volt power. Of course, if you're using something that's wireless that needs a battery, again, you only need the one screw terminal because there's no power daisy chaining in that case. And of course, for wireless devices, again, just a battery powered thing. We'll talk more about that later. But essentially, the different functions that were ultimately come up with, or that we came up with as we designed these boards, were power selection and regulation. So there'd be some sort of switch to either select external DC power for when you actually are using the board in the field, or for 5 volts from the USB when you're programming. And of course, there'd be a 3.3 volt regulator. Note that for some things, there is also an additional 5 volt regulator if 5 volts was needed for something. Programming circuit. So this was the initial implementation of the microcontroller programming interface. So it used an FT232 chip to go from USB to UART. Then there'd be some additional switches for selecting whether the radio or the microcontroller was going to be programmed. And then, of course, a 4.7K resistor to create the serial UPDI implementation. So UPDI is the programming interface on the microcontroller we're using. There would be channel and UID setting switches. So these would be some 8-bit wide dip switches connected to some shift registers to have less wires run directly to the microcontroller. And then, of course, some 10K bust resistors to create a pull down to keep things from floating. There, of course, there'd be wired network interface, so that would just be your RS-485 transceiver, the SP3078. And then, of course, your RJ45 jacks, and if necessary to go to the outside world, then also an RJ45 waterproof coupler of some sort. And then, of course, some other necessary passive components as well. Wireless interface, so that is your XBee or Zigbee radio. Some sort of low battery detection. So basically this ended up just being some sort of resistor divider that feeds directly into the microcontroller's ADC. There, of course, would be buttons for certain things that, like on the Marshall controllers. So these would use some JST connectors to plug the buttons into. And then, of course, we designed up an RCD bounce circuit. This should have done a little more prototyping with that, but it still worked. And sorry, this should actually say isolated resistor pack, not bust resistor. And then that will also use some discrete capacitors as well. LED indicators, so just LEDs and some isolated resistor packs. Can't say that, remember this was a bust or isolated resistor. Anyways, and then of course also the LEDs would plug into some JST connectors as well. 7-segment digit driver would use some TPIC 6C596N. So if you notice the 596 in there, that's because this is a serial to parallel shift register that has some special relatively high current open drain outputs on it that allows to drive some very large 7-segment digits. And then, of course, so 15 ohm resistors for current limiting. And then a CD 4109 because everything operates at 3.3 volts, but the shift register chip is an older design, so it needs 5 volt logic. So this just acts as a logic level translator. The actual 12 volt LED light driver. So to talk about that, there's two versions of the light driver. So for the low side version, just a simple N-channel MOSFET with a relatively low, with a quite low RDS on, just in a TO220 package to make sure things don't get hot. The high side version is a little more complicated. It's a P-channel MOSFET that does the primary driving, TO220, and this is what actually that's what drives the LEDs. And then an N-channel MOSFET to pull the P-channel MOSFET low. It's just a small one that in a TO92 package, and this drives the P-channel from the microcontroller. Of course, we also wanted to be able to sense if a color was not working properly, so we have a 0.5 ohm current sense resistor in there. And then, of course, also finally an Adafruit Stemma QT interface. So this just uses a surface mount 1mm JST connector, and that connects to the I2C interface on the microcontroller when necessary. So talk about the signal light drivers. So we didn't pick the LED modules. The client provided us with LED modules that they had previously worked with for building the pit lane light. So first they had a 4-color red, yellow, green, blue light, which uses common negative wiring. So basically you have a common ground, and then each color needs to be connected to a positive 12 volts to turn on. Then they also had just a red, yellow, green, or 3-color light that uses common positive wiring. So basically you have a 12 volt line, and then each color needs to be connected to ground to turn on. This, of course, required 2 types of driver boards to be made, as discussed already. So this ended up being signal light low side driver, not acid, which is for the common positive type of light, and then signal light high side driver, which is for the common negative type of light. And then each of these boards can have 2 configurations. So wired, which uses the RS-485 interface. Note that this is a higher power load. So this uses the 12 volt supplemental power, where you have power coming in on your screw terminals, and of course you have to have both of them populated to do power daisy chaining for the next device. And then of course there's also a wireless version which just uses a Zigbee, and then is of course powered just by a battery. So then to talk about the wired versus wireless implementation in a little more detail. This is just in general, not just for the lights. So any board that's wireless has an XB radio. These radios are assigned a 64-bit unique address from the factory. This gives boards with an XB a unique address that we can use to address them. Wired boards, of course, do not have an XB radio, but we still need a way to address them. For wired devices, we added a second set of dip switches to set an 8-bit address, which is called the UID, or unique identifier. For devices that have wired and wireless versions, such as lights, we can have footprints for both the XB radio and components for the wired part of the network on the same board, and then we can just populate as needed. And heck, we can even overlap certain components that only ever are mutually exclusive to each other, depending on board version. And this way we can also save space. So the light driver boards, they actually implement these following functions. So they use a power selection regulation, programming circuit, channel, and UID. Again, channel, just channel if it's wireless, but then channel and UID if the light is wired. Of course, the wired interface, wireless interface. Now, in this board, of course, they are mutually exclusive to one another, depending on configuration. Low battery detector, and then a 12-volt LED light driving circuit. So this is the first version. This is the low side driver light for just your 3-color light that they currently have. Now, of course, you can note that we did set it up to be able to do 4 colors anyways. We later modified this board a little bit so you could tell it if it's a 3 or 4 color or not, just by shorting a pin on the microcontroller to ground. But basically with this board, so I'll talk about this a bit. So first you have your 4 N-channel MOSFETs here, and your 0.5 volt resistor for checking if the correct amount of current is going or not. This is the microcontroller here, USB interface here, USB to serial or UART here, power selection. These are the RJ45 jacks, plus this is for the wired configuration. This is your wireless radio here. These two switches here and here are for programming selection of whether you're programming the radio or the microcontroller. And then these sets of dip switches and shift registers down here are what implement the channel and UID setting stuff. And then this connector up here is what you actually screw the wires for your light into. So then we can show the board here. It's might make a little more sense seeing it here. First things first. For this presentation, I turned off the ground plane when I took the pictures of these from the design software. So don't worry about that in the actual production and implementation of this. We do have ground planes on both the top and bottom side of the boards. So don't get mad at me in the comments there. But basically, to start here, so again, you got the two screw terminals here for power input. Again, one is only ever populated if it's wireless, but then the other one down here will be populated to pass power on to the next device that needs 12 volts. This is the big switch for power selection. The big regulator here for getting 3.3 volts. This USB and these switches, this is for programming interface and actual programming selection. Microcontroller here. These are the N channel FETs for the low side driving version here. This is the actual current sense resistor. This here is the terminal for hooking up your lights with. And then these two sets of dip switches here are for your channel and UID selection. And then this down here with the transceiver chip here and these RJ45s, that is for your wired network interface. So to talk about wireless versus wired implementation, to talk about if components are populated or not. So again, when you're doing wireless, you have just this dip switch set here with this is the resistor pack, this is the shift register, and this is the actual dip switch here. And then of course, these two smaller headers here and here are for plugging your radio into some little round machine headers. But if you're doing wired, then you add this second shift register, this second dip switch, and then this other resistor pack here. And then that allows you to set your UID, and of course you populate the rest of the wired interface here with this transceiver chip and these RJ45 jacks. Oh, also a nice touch, we did also put a little Southwest Car Club logo on here as well, on all the boards. So then this is the same kind of board, but this is for the high side driving version of lights. Again, of course, you have all four colors available. But basically, top row MOSFETs are the P channel MOSFETs. And then attached to those are your N channel MOSFETs to pull them low to turn the P channels on. And of course, the actual N channels are what connect to the microcontroller here. Again, and then all the other circuitry is basically the same. So now we can see that here, you can just see the only difference between the low side version and now the high side version is just that the light driving section is a little more complicated with having pairs of MOSFETs connecting to each other. So now talk about Marshall controllers. So again, Marshall controllers have power selection and regulation, programming circuit, just the channel settings, which is because these Marshall controllers are only wireless. Wireless network interface, there's no wired interface, of course. Low battery detection, buttons, and LED indicators. So in this one, of course, again, USB, power selection here, channel switch, USB to serial, your two programming switches for microcontroller and radio, power regulation there. Then up over here, you have your input buttons for green button, blue button, yellow button. And then your indicators over here for green indicator, blue indicator, yellow indicator. Then this is your association signal. So that comes directly from your XP radio. When connected properly, it just flashes at a steady rate. That's to tell that that the network is working. And then there is this status line from your microcontroller that's always just solid, and it'll start blinking depending if it has a low battery or if a light that it's attached to has a low battery, depending on the blinking rate. So then here's the board here. Again, you can see some of it, it looks similar to the light boards that we had before. So again, power switch, power regulation, USB programming interface, programming switches. Again, just a spot for a Marshall controller, or not for the Marshall controller, for the radio. Channel selection, all these different JST connectors here for your different buttons or indicators. And then, of course, you have, this is a bust resistor or not bust, isolated resistor pack for your RCD bouncing, along with these resistors here and capacitors. So, and then current limiting for the LEDs. Master controller main. So this is, of course, a very important board. So this drives the wired part of the network. We're using a round-robin protocol of sorts. It also translates messages between the wired and wireless parts of the network. Has a second microcontroller on it that intercepts error messages and puts it on a graphical user interface display. More on that later. Then, of course, it takes 12 volts from the power supply and puts it on the unused pairs in the wired network cabling to supply power to low-power devices, such as button modules. And then, of course, separately from this, you also have connections for the supplemental 18-gauge wiring that powers high-powered devices. So the master controller main board functions, so power selection and regulation, of course. This is a little more complicated because it has 3.3 volts, but then also 5 volts for that GUI display that's needed. Again, the programming circuit is slightly more complicated because you have two microcontrollers instead of just one. Wired network interface and wireless network interface, so these operate in tandem on this board. Low battery detector, and then LED indicators, of course, depending on what the master controller main board is being used for exactly. So here's a schematic. So power switch, power regulation, programming selector switch, USB and USB to UART stuff over here. Wired network interface stuff here, and you can see the power injection with some fuses for that as well. This is the menu microcontroller that'll be connected to the GUI display over on this connector here, and some spare GPIO from the menu microcontroller as well. Then there's the actual coordinator microcontroller. So this is what drives the wired part of the network and also intercepts messages from the wireless part of the network and does the translation. This is of course, the battery level sensing circuit here, and similarly on the other stuff before. And then, of course, this is the wireless interface here. And then this is the circuit board for it. So wired stuff here. This is the power input for it from the power supply that's inside the enclosure. Wireless radio. Again, USB programming here. Power selection switch for whether you're actually programming this board or whether you're actually running it for real in the field. 3.3 volt regulation, 5 volt regulation here. This is the connector for the display. These two resistors are for logic level shifting to make sure voltages are compatible, etc. So button modules. So the idea with these boards as we went along to implement all the different functions in the distributed control system of the master console was that we could just make one generic board or module, and then the software that's running on each of these button modules and what headers are populated defines what function it does exactly. So it could take on the role of a lap count controller, e-stop or red flag controller, a generic sector, start line, which is basically just the same as a generic sector, pit lane controller, which is just basically a special sector. And then, of course, these button modules are low power loads, so they're powered by the wired network cabling. So the button modules implement these following board functions, and exactly what's populated here depends on what function the board is taking on exactly. So again, power selection and regulation, the programming circuits for programming the microcontroller, channel and UID setting switches. Of course, these button modules are only ever to be wired, so there's no wireless implementation for these. So of course, they need both the channel and UID. Of note, you can think of these button modules, particularly when they're being used as a sector controller, these act as counterparts to the Marshall controllers out in the field. Wired network interface, low battery detector. Actually, no, we never implemented that. I should have nixed that from this slide, but oh well. So these didn't actually implement low battery. LED indicators, of course, buttons, because you need buttons, and then a stemma QT interface, depending on what you're doing exactly. So microcontroller, on these modules, of course, you can have up to 5 buttons we determined is what would be needed. 3 discrete LED indicators if needed. Power regulator here, and then USB UART, USB interface over here. This tiny connector over here is your I2C stemma QT connection for when you connect up a alphanumeric display to this. We used an Adafruit one. This is the wired network interface. In this case, you can see the connections for your RS-485 12-volt supply. Power selection switch, channel, and UID over here. So then, of course, what was it? So then you can see the board here. So you can see the RJ45 and wired interface over here and how these do supply power for these boards. USB interface for programming here. There's no selection switches because, of course, you only have one device on here that's being programmed. Channel and UID selection. And I guess to clarify from my earlier slide, there is no low battery detection. Again, this isn't operating off a battery, so you don't need it for this board. And then finally down here, you have your tiny little JST 1mm connector here. That's for your Adafruit alphanumeric display. And then finally, lap count driver. So the original idea, and I'm glad we went away from this, was to use a gas station price sign display for this. So one of those big honkers that you see at a gas station to see what the cents per liter is. So then the driver board will more or less act as a translator between our wired network and what the sign needs. Braden redirected us, and we also kind of realized that the whole gas station price sign thing was a dumb idea. So he redirected us to something else, and we then realized, oh, that implementing our own large 7-segment display wasn't as difficult as originally thought. So this was that gas station price sign here. Again, this was on AliExpress, so also not a good idea. But ultimately, we came across, Braden pointed us to this 6.5-inch 7-segment display. For these, you could get little backpack drivers that could solder onto the back of these. But we more or less made our own board that was based around that SparkFun design, and with some slight modifications. But the lap count driver board now implements these functions: power selection, programming circuits, channel and UID setting. Again, this board's only ever meant to be wired, so you need both the channel and the UID. Wired network interface, and then 7-segment digit driver. So that's where that gets used eventually. So here's the board for it. So again, microcontroller, USB here, and USB to UART here. Channel and UID here. This is the wired network interface. And again, this is a high power load. So these jacks don't actually take your 12 volts and ground to power anything. This is that CD 4000 or 40109 chip that acts as a logic level translator. This is your 5-volt regulator here because these chips, of course, are older 5-volt logic. These are your connectors for connecting up all your digits to the chips. Then, of course, we can see the actual board here. Again, power selection, and of course, you need 2 of these screw terminals for daisy chaining power. USB interface for programming, 3.3 volt regulations, 5-volt regulation here. Microcontroller, this is the voltage level translator. Wired interface here. Channel and UID selection switches here. These are the driver chips, and then the connections for plugging your digits into. And then, of course, all these little 15 ohm resistors for current limiting that was based off the SparkFun design. Okay, so now starting in the second semester here. So this is kind of a timeline of, so January was compile, bill of materials, order the boards and parts, start on PCB assembly. And then initial decision on how the wired network protocol was going to work exactly. February, we finished board assembly, and then we did some initial programming, and this is also where we were like, okay, yeah, and we migrated from Arduino to MPLAB X. This required us to change our implementation of UPDI. So February, still, again, this is where we needed to make a bunch of hardware changes due to the programming interface. Again, this took a lot of time. And then did some additional testing of the Zigbee radios at a distance of 250 meters. This happened at the University of Regina parking lot 1 to be precise. I guess I should say, previous to this, we did also I did some testing in December, just in the backyard, or not in the backyard, park behind my house. Got some mixed results there, but this confirmed for us that yes, we could actually get these to work at the distances that we need to. So March, we also finished our changing the hardware around and our bodges. So this is where we could truly actually get a good handle on the software. A lot of the software was handled by Michael. He was most competent with embedded programming. Lucas and I did give some ideas here on how to do certain things as well. With software, because of the complicated nature of our system, and with the timing and everything, basically everything just ran on free RTOS. So we use the real-time operating system to coordinate all the interrupts and timing and everything. And then things were designed around a modular block approach. And then towards the end, there was some spaghettiing code just to catch weird edge cases, things like that. So then, with those board modifications, we did go ahead and revise the boards to look like this, or these are after to reflect the changes that we made to the boards that we had, and then these will more or less be what we give to the car club for future builds. So then, finally, towards the end of the second semester in March, there was enough software built that we could do a basic demo for the faculty right at the end of March, is when they did faculty demo. This allowed us to show this faculty, okay, where are you at, and then what things you would need to fix and get up and running for when you actually did project day, which was here at the beginning of April. So the demo, we were able to get the things working a little bit better by then to have a basic demo for actual public project day. Parallel with our second semester, we worked with the Kart Club president, Dave Goulash, to work on enclosures. Dave happens to be the owner of Regina Metal Industries, a metal fabrication shop just outside of Regina. or just on the outskirts. So again, of course he handled enclosure manufacturing. Certain enclosures were designed by us, and then maybe David, but then other things were exclusively handled by Dave. So we'll talk about that here. Again, enclosures were kind of outside of the scope of what the university was marking us on, so it was good that we had him around to help us out with this stuff. So a reminder of items to be built. So wireless lights, Marshall controllers, start line or wired lights, portable race director controller, pit lane light driver driver and controller, last lap lap count display, and then the master console. So the wireless lights. So all wireless lights use the 4-color red, yellow, green, blue light. So these all needed signal light high side driver boards. The enclosures were handled by Dave for this one. So he used some old traffic light module enclosures, and then he added some custom welded aluminum parts onto that. To power those lights, we used some lead acid batteries, similar to what were used by the car clubs for the carts. So basically, I can't remember when this happened exactly, but Dave one day sent us an email and said, hey, here's a link to a battery from Princess Auto that is similar to what we use in our carts already. Can you use this for the lights? So when we checked it, based off its stated reserve capacity and the definition of reserve capacity, we calculated that its capacity in amp hours was about 12 and a half. And then we did some estimates at the time of current draws for all of our equipment, and deemed that we could get a very good amount of runtime out of those, about a few multiples of what we needed for that 10 hours of runtime. So then we deemed that okay, we could use those lead acid batteries for the wireless lights. So here's wireless light. This is kind of very early when Dave partially had it together for us. This is now at the end of the semester. We only had one light, and we had to continue to work with him to get the other two. It just took time, but basically, so you can see again, light module in the middle there with a little adapter to make it fit to the actual traffic light module. Then it's on a little aluminum pole, and then a little spot to put your battery. And then, of course, at the top, you might just be able to see a hole for where your antenna would stick out of. So then here's that one that's a little more assembled. You can see the battery at the bottom. The wire for power just goes up through the pole in the center. And then you can see the wire, it comes out into the inside there, and then into the one terminal. Again, just one terminal because this is a wireless light. Zoom in here a little bit more. We can see the actual board, and then this is just on a little adapter plate that's glued into the enclosure, and then on some standoffs from the actual mounting board. And you see up towards the top of the board where the light screws into. Because this is a wireless board, you can see where the wired stuff is not populated, but then you can also see the smaller headers for a radio. And then you can see the radio plugged in this slightly zoomed out version of the picture of it. So then Marshall controllers, again, these just use a Marshall controller board. So the enclosures were designed by us and then manufactured by Dave with some slight modifications. And then, of course, we used an 800 milliamp hour LiPo battery of the 3S or 11.1 volt variety. We deemed that should be good enough, or more than plenty. And it ended up being more than plenty later once we did once we got some more accurate numbers. So this is the original design in CAD. This is of course just the body. There was also just a blank lid that would go on top of this. So then you can see here the controller without the lid on it, and then the lid, you can see it would just screw into where those holes are there. You see the board put in there, buttons populated with the radio, and then the battery is loosely sitting in there. We later made something to put the battery in there a little more securely. This is here a different angle of the board thing with a little less, or with it a little less assembled. And then you can see the lid sitting off to the side there with some screws. So the start line lights. So The three lights would consist of, on the top, a red, yellow, green. So of course that requires a signal light low side driver board. The middle light we made a 4-color one, which would be, so that requires a high side driver board, and then the bottom would be another 3-color light. We wanted one of these lights to be at least have blue available, so you could treat that front straightaway as like a proper sector and be able to signal to drivers, hey, pull over, so somebody can try and pass you. And then, of course, as stated earlier, these three lights would be wired back to the master console, and then each of those boards would be daisy-chained to each other inside the enclosure, as discussed earlier with how the wired network works. Because, of course, these are high-power loads, they would also have separate supplemental DC power to power these boards with. The enclosure, of course, this was handled by Dave. He took 4 traffic light module enclosures and ganged them together. And then there, of course, there's some custom end caps for those with some cutouts for mounting, some Cat5 couplers, and some SD20 power connectors for the actual supplemental DC power. Now, of course, you'd note there was only 3 lights. The 4th housing on the bottom would be for the lap count display and driver board. But then you can see when he eventually got it to us, this was what it looked like without the lights installed in it. I took care of putting the lights inside of there. So that's that, and then you can see on the bottom there is the actual lap count digits already. He put it in there for us and made that up. So, portable race director controller. So the original idea behind this was we were going to use a modified Marshall controller. This wasn't going to work after we designed the Marshall controllers and realized, okay, we could not do that functionality that we originally wanted. So the final design was to actually just make a cut down master console. So master main board, and then that way connect up to 2 button modules, one for e-stop and a generic sector. Again, this was kind of, reusing the same design, but to make something a little bit different. And of course, this would not have a graphical display, but instead modified to have some little LED indicators for some stuff, such as network connectivity, etc. So then here's the original enclosure design for it. You can see where the master board is, system stop, and start line card. Here's it partially assembled without any of the wiring done. And then the pit lane driver and controller. So the original idea with the pit lane light, we were going to modify the existing pit lane light by adding a low side driver board to it. We would then remove the existing wiring that was out there and permanently retire Braden's controller. Then we would run Cat5 from the pit lane light to the timing booth with the button module linked to a pit lane light, then to the master console. This way, you could have the race director control the pit lane light, but then also the timing person, just in case the timing person needed to for some reason. The final design wasn't quite the same as that. Talking to Braden, he didn't want to remove that existing wiring that they had for the light. So what we compromised on was we would take that light driver board, instead of putting it in the light itself, we would put it in the same enclosure as the button module that is in the timing booth. So that's fine. And then, of course, this would also be handy. We could swap Braden's controller back in for if we needed to for some reason. So this is that box with the low side driver driving board, and then, of course, a pit lane controller card living in there. This is the original assembly, but you can see a potential issue with it where I can't fit the Cat5 couplers in there, and also have the actual little Cat5 wiring for stuff. So luckily later, Dave was willing to remake that box, but make it a bit longer, and that way we could fit the Cat5 wiring inside there. So that was good. Admittedly, I could have actually requested it to be a little shorter, but hey, that turned out all right. And then on the front there, we did end up adding on a proper connector for connecting the light with. And then of course the lap counter, that was designed by Dave, and then of course we already noted that it was in the same enclosure as the start line lights. So then finally the master console. So again, it's designed by us, and then it was built by Dave with some modifications. So it consists of a 12-volt power supply that goes from, that connects to the generator. One master console or one master main board. So that is what, intercepts the messages on the wireless and then works and then drives the wired part of the network, etc. The master console can accommodate up to 7 button modules with the stock configuration that we gave them for the different functions, but they can add 3 more cards, so up to 10 cards, for expansion later. Then of course it has 2 Cat5 couplers for the wired network, and 2 SD20 power connectors for supplemental power supply. So then you can see here, there's the power supply, then the master main board, and then you can see where all the different button modules are supposed to be situated, and what exactly each one is. So lap mount control, system stop or emergency stop, that's the red light controller. Button module, button module, but this one's for the pit lane. Start line, sector 1, sector 2, sector 3. Then of course, all these different extra ones that are for expansion later. This is the lid for it. So unlike the Marshall controllers, where we had everything or all the board and then all the lights and buttons just on the same body piece, and then the lid be blank. That way things would flex less. That wasn't really possible with this, so we had to put buttons and lights and stuff on the lid, and then make sure that we made up a proper wiring loom that was flexible, so you could open and close the lid easily. So then we can see here, this is the initial thing, body part for the master controller when we got it from Dave, and some of it just at the very beginning of assembly for it. Then you can see this is more, somewhat mostly assembled here, or partially assembled, and you can see the wiring loom that we got going there. You see here it's somewhat completed, and this is for getting close to faculty demo and project day. This was much later in the summer when we were doing other tests with it and getting things closer to being workable, or basically working at this point. And then here it is actually fully assembled with some changes that you can see. And then of course the actual spots for extra stuff later have just been sealed off for now until the card club needs them. Okay, so just to continue the timeline side of things here. So May through July consisted of a rework of software to get the wired network working very reliably, and then also to build upon that, implement the wireless parts of the network a little bit better. Microcontrollers, we worked with those a little more to optimize them a little bit better and to get them to run a bit faster. Lots of testing happened, both May through July, but then also later to hunt down bugs in the software and to catch edge cases. We continued to work with Dave to get enclosures manufactured, and then we also changed from Zigbee XBee-based radios to XBee radios that implemented DigiMesh. So Zigbee, it's a more open standard by many manufacturers, but it had the problem of a fixed user-defined central coordinating node. This in particular bothered me because if that coordinating node goes down, then you might have issues with adding things to the network later if needed. And I just didn't like the idea of that. And then of course the cart club would have to keep track of whether the radio being programmed would need a coordinating profile or a regular profile. So ultimately, and I wish we had found this earlier, we did switch over to XB radios that use their proprietary DigiMesh protocol. In this case, all the nodes are the same, and they operate more or less as a straight peer-to-peer mesh networking protocol, where the coordinator actually gets elected at startup when all the nodes find each other. So that's handy, and it also, in our view, would make things a little more reliable. And then also, you'll need to keep track of one type of radio profile rather than two. So in August here, again, we've kind of finished certain bits of hardware troubleshooting that we needed to do if we found little bits of problems. Again, we finalized things with Dave to be able to get all of our enclosure equipment from him. And then during the summer, equipment was mostly at Michael's place because he simply had the space for it to be able to work on it and to really troubleshoot the software. And then, of course, he needed to get that stuff out of there at the end of August, so I took that stuff to my place to finish testing things and to finalize putting stuff in enclosures. So at this point, of course, before at the end of that semester, we had like the master console, one Marshall controller, and one light. Everything else was still bare PCBs. And then we had the light modules to hook up to them. So that was good enough for testing. But then eventually, once all the stuff was moved to my place, we were able to assemble the rest of those lights and fully test everything in their enclosures. So again, September, that actually consisted of putting the lights together, and then put the lap counter in the enclosure and test. Then some final distance testing happened at the parking lot of Rosewood Church. So again, they're relatively close nearby. I know a good number of people from there, and also their parking lot is very large, and so is a good simulation of the distances that we would need to deal with at the track. If I recall correctly, their parking lot from end to end is about 180 meters across, which is more than plenty for testing the lights. And then, of course, we did also work on making some plastic battery holders for the Marshall controllers. With that, now I will show some video footage here of testing of the various lights with one Marshall controller, and then also showing the master console being tested with the wired lights and the race director controller here in just a second here.
Okay, so here's me testing out the Marshall controller with some wireless lights. So let's turn that on there. Now it's important to note that yes, these are being tested here just in their enclosures, but that all of these boards and things were tested much earlier, prior to them being installed when everything was still over at Michael's place. So this isn't the first time these lights have been tested. What this demo also shows here that you can have a Marshall control multiple lights. So that's just important for future expansion later. Important note here, I press a button, and the first time that you send a command, it does take a few seconds, but then after that, the timing is perfectly reasonable. So you can see now on the second go around, it changes almost instantaneously. There we go, there's blue with the flashing. There we go. And then back to blue here, and then more yellow. And now here's the test with start line lights and lap counter / last lap indicator. So there, I booted up pretty fast. And then the race director controller was thrown in here as well. So we'll just give it a few seconds to boot up, as it is a little bit slower than everything else for some reason. It's not too much of an issue though. So while that's doing its thing, I just got to get my camera angle adjusted here. And also when I was shooting this, my camera was acting a little bit funny from the looks of it here. At least when I'm recording this voiceover. So first thing to do is to zero the lap count display. Or not yet. Just gonna get my camera angle adjusted there. There we go. So we press the 0 button. Go 0. Perfectly reasonable. And then we'll increment it a bit. 3, 4. Okay. There's a little bit of a problem with the RCD bounce, but that was worked out. 8. Then halfway, we press the halfway button there for HF. And then we continue to increment after that. There we go. And then LL for last lap. And if you press the up button one more time, you can get it to display FN for finished. Show that here in just a sec. There we go. See, FN for finished. This is an extra little bonus. And then you can zero the display again and reset it. And then press the down button to just turn the display off. And here now we'll test the start line lights. So test them from the console there. Spawn perfectly good. Now only the middle one is blue, so it's the only one that flashes. And then the other ones will just stay green if they receive a blue command. So that's how we design the software. And now to do it with the race director. So it took a second there just on the first try to send out the yellow. And then with the race director controller, the confirmation response is a bit slow, particularly if it's the race director controller sending the command. But again, that's not too big of a deal. So you see the master console has confirmed, but the race director controller has not quite yet. This does take a minute for it to confirm. Just waiting for it here. Okay, there we go. Now it has confirmed. So now we can do a green from the console. There we go. And then when it's initiated from the console, the response is perfectly fine. So there we go. I'm pointing that out there. And then we can do a blue from the race director controller. And that sends out perfectly reasonably. You can just see the flashing there from the console. And then you can see now I'm looking at the light here, doing its thing. And then it does take a little bit to confirm. There we go. Now it's confirmed. There we go. And now we'll do an e-stop all red from the portable race director. See, that responds perfectly quickly. Now it just has to sit there. It blinks until it has gotten confirmation messages from all those lights that they've turned red. There we go. And then because this console didn't actually have its button pressed, its red light will just stay blinking, which is how we program the software. If the button was pressed on the console and not on the race director controller, then it'd be the opposite for the light blinking. Now I've unlocked it, and then it does take a few seconds, and then all the lights go back to the safe color of yellow. And then everything just reconfigures there and unlocks.
Okay, so after the demonstration of some of the equipment just in my basement, and to show things working in their enclosures, here's also the pictures that I got from the test at the Rosewood Church. So I did drag my parents along to help me with this one. So you can kind of see the three lights. Two of them are relatively close up there, and you can see kind of out on the right side of the picture, kind of near the the Honda Pilot there, and a little bit distance, there's the third one. So this is kind of to simulate some distance between the different lights, but then still so I can also see all three of them. Unfortunately, I didn't get very good pictures, and I forgot to take video of this as well. But you see this is halfway across the parking lot, and you can kind of see the lights out there. And then this is at the other end of the parking lot. Again, it's quite a large distance. And then you can see here's the master console working. Fortunately, I lost my pictures of the lights working, and you couldn't see them very well anyways because of the distance, just because they look quite small. But the test overall was a success. So then finally, we were originally hoping to do commissioning on September 22nd. Weather was not permitting. So finally, we commissioned and tested the stuff at the track on October 6th. So then here's some pictures of that. So this is the actual start line stuff where you can see the 3 lights and the lap count display. And then you can see out in the distance there's a light. Zoomed in here. Another light. I can't remember if this is the same light. I don't think it is. Yeah, this is probably light 2. I'm not quite sure. Here's a Marshall controller. Eventually, we did swap in some smaller antennas for these Marshall controllers, just because the big antennas were quite comical on those Marshall controllers. But we still kept the big ones for the master console and the actual lights. So this test overall was a success. So we did complete. So of course, we actually did complete the project. Again, it would look kind of bad, if we just abandoned this after the semester was over. Of course, the car club did have a backup plan just in case that did happen, where Braden would take over. But ultimately, it was also done out of a duty of care to the client, based off our ethics class, and we did get compliments that Braden told us that we managed to impress Dave. So that's good. So this was pseudo planned out for the most part, but here is a formalization of what the actual wired network looks like once everything was hooked up. So again, you got your master console or master controller here, or master console. So master main board, lap count controller, pit lane controller, sector 1, sector 3, sector 2, start line, and emergency stop, and that's just the way based off how the Cat5 cable is routed inside that controller. Of course, you have a small power supply here that injects 12 volts to the master main, but then also onto the supplemental power. Again, this connection here is not quite accurate, but it was just to simplify things in a certain way. So supplemental power goes out for other things here to connect up to the start line and lap counter, which of course they all take the supplemental power because you don't want to power them off the Cat5 cabling. You can see through the whole thing, of course, the Cat5 cabling runs, and then with 120 ohm termination resistors on the end there. And then on the other side, of course, you have your pit lane box with your pit lane controller, and then the pit lane driver. A slight last minute modification that we did was, rather than have the actual driver board run off of the supplemental power, I did just quickly grab a little 12 volt power supply and use that instead. That being so we could save not have to have such a long run of DC wiring just to go to this pit lane box, since it's quite a ways away for all the way along the catwalk into the C-can. And then of course there was a question of, because this pit lane controller card is powered by the Cat5 cabling, there was quite a distance between the pit lane box and the master controller. So that worked, and I had somewhat tested that beforehand at home. So that worked out. But glad to see that working. I don't have a diagram of the wireless network, but it's basically the same as that diagram that I showed earlier of all the distances, just with some other dots that would be added onto it for the actual lights right at the corners. Okay, so were our specifications met? Minimum 10-hour battery life, more or less, yes. The caveat being, of course, this was calculated based off actual current draws of tested devices. Basically, I connected the multimeter in between the battery and then the device, and then based off the current draw and the battery capacities that we had figured out earlier, we figured these various run times would be in the ballpark of how long they'd stay on for. Of course, with the Marshall, you can't just sit there for 88 hours and wait for the battery to die. So that's the best we could do for testing that, but it seems reasonable. A response time of 1 second. We realized during our second semester that this would be very difficult to actually properly test or quantify. You'd need a high-speed camera of some sort to figure this out, or some other way of doing it. I had made up a little tester, but of course, you still need the sending and receiving device to be in relatively close proximity to hook up probes. So it seemed kind of an unreasonable test because it doesn't take into account distances between nodes and the actual placement of them and the actual connection of the mesh network on the XP side. So basically, from previous video testing and demonstration, minimal to no human perceptible delay from when you push a button to when the lights turn on. Of course, once the network is established and you send a command for the first time. So we considered that good enough, and the client was happy with that. Wireless range of at least 200 meters. Again, lots of testing was done through various points in the project to make sure that the wireless radios would be able to do the distances that we needed to, and they ultimately did. And that was all ultimately confirmed at the Rosewood test and then also actual commissioning at the track. So the IP54 enclosure. So we used waterproof connectors, buttons, and switches wherever we needed stuff protruding from enclosures. Again, we also made sure minimal items were protruding from enclosures to reduce points of ingress. Again, this ultimately means, though, there was no external power switches or charging ports. So you have to take the batteries out, but that was a compromise the Car Club was fine with. We did recommend to the client that they create rubber gaskets for enclosure lids, etc. Again, this was not done at the time of commissioning/install. And the client had indicated to us in an email that just on rainy days, they would just roll back to their old system where they'd swap and bring the controller and just use the flags. So that's fine. And of course, lights and lap counter are visible on a sunny day. With the LED light modules, again, they were already used for the pit lane light. So that was fine. Well, that was kind of a given that would work. Working with Braden on those 7-segment digits, we did look at the specifications and listed stuff on the SparkFun website as well as in the datasheet provided, and he determined that yes, for the distances on that front straightaway, that those digits should be perfectly visible to drivers. So that's fine, and that would work. Of course, we recommended for the lights that the client install some sunshades, but again, that's just kind of optional. And from those pictures of the commissioning, they seem to look just fine out in bright sunshine like that. So that was fine. So were client requirements met? So some more extra features that we had tried to put in, we ultimately could not implement for various reasons. First one was USB programmability, and then the master console error message graphical user interface. So the USB programmability, that was desired by the client, so they wouldn't need to fiddle with proprietary programming equipment, boxes, and cables. This was not possible once we migrate to MPLAB X because Microchip requires that you use their proprietary programming box. So, again, this is a lesson learned in over-promising and then under-delivering / researching what you need to do to make your hardware work. So they were fine with that, and it wasn't, too bad in the end, the way it was implemented. So the error message GUI, this was designed by us as a user-friendly way to verify error messages sent out by equipment indicating low batteries or burnt out colors, things like that. This is ultimately backed up by status indicator LEDs on the Marshall controllers. They would just flash at certain rates if something was wrong either with the Marshall controller or the connected lights. Ultimately, the GUI was not implemented due to end design of hardware and software, which made it difficult to route messages to the controlling microcontroller. So to explain that, the display was controlled by the menu microcontroller on the master mainboard. This part worked. Michael was able to work with me on the display, and we were able to get some pseudo test messages from the menu microcontroller to go onto the display. That was fine. But the menu microcontroller was interfaced to the coordinating microcontroller on a separate UART from the rest of the wired network. This is where problems began due to ultimately how the coordinating microcontroller software was written, and this made routing messages to the menu microcontroller quite cumbersome and put quite a bit of load on the coordinating microcontroller. Ultimately, the menu microcontroller should have lived directly on the wired network, either as a separate button module or just connected directly to the wired network UART of the coordinating microcontroller to intercept any kind of error messages. So again, this is kind of a lesson in over-promising, under-delivering, and then also better thinking through the process of how to implement certain things. Again, at least we have these status indicator LEDs as a fallback, just in case. So talking about the GUI just a little bit more, I did use a Nextine display that came installed in this one came installed in an enclosure with a rubber gasket. I had used these before on a couple projects. They're relatively easy to create a GUI for. They use a design environment similar to programming in Microsoft Visual Basic when you're designing those little actual window application interface type things. Kind of a good thing, I guess, with these Nextions is because it didn't get implemented, we didn't really know how reliable it would be being outside in the environment we were using it in, even though it was like in a proper enclosure. So getting rid of it, one less thing to fail, in a way, it does increase the overall reliability of our system to a degree. When it first started up, you would have Sosa's Kart Club logo load up, and then when it got the good signal that everything booted, it would load this default screen. Things would get populated on the screen. If an error came in, it would get populated. There's up to 5 errors on the screen at once, and you could scroll through them. You could select to clear a particular message, and then various commands would be sent around to ultimately wipe the error out of the system and refresh the display. Despite these two features not being implemented, we did ultimately still meet the client requirements that were originally set out for us in the fall 23 semester of wireless lights. So 3 of them, 3 start line lights at the race director tower, a lap count display at the start line for drivers, and then a light up last lap sign to replace that physical swing L1. Also of note, after shoring up with the Kart Club with invoices and accounting for parts that were either exchanged or not used, we came under budget by about $400. You can see the exact figure there. So at this point, the hardware has been commissioned. That's over. But at this point in February of 2025, we still need to brush up the documentation for handover to the Kart Club before the 2025 season starts. The client was also going to work on some of the following items here. A swing mount for the start line lights and lap count display enclosure. This way, it could be swung around to face either side of the pit lane, depending on the direction of the race. And then also a shelf mount for the master console in the race director tower. Originally, we were thinking there'd be some sort of hook things on the master console itself, but then Dave decided to change that and just make a little shelf for the master console to sit on instead. So that was fine. And then, so that's still being worked on by Dave. And then some sort of mount for the master console magnetic antenna base, just for it to stick onto, so it sticks up perpendicular to the ground for optimal reception and placement. And with that, this presentation is finished. I hope this was informative of what this project was, how we eventually got to a finished product, and also some lessons on things that could have been done better. And just again, for those that I might send it to that are in engineering and that aren't at their 4th-year project yet, I hope you found this helpful. Just generally on how capstone projects kind of go. With that, see you later.